Hello everyone, I'm back again, and I'm here to talk to you about the integral test and estimates of sums. Again, my name is Jamie Mulholland, and I'm a lecturer with the Department of Mathematics. So, we've just looked at series, this idea of adding up infinitely many numbers and trying to make sense of what that even means in terms of, do the numbers, when you add them all up, does the sum of, or these partial sums, do they go somewhere? Do they converge? So does it make sense to add up infinitely many things? And that was this whole idea of a series and whether the series converges. And in the case where the series doesn't converge, where these partial sums don't go to a particular number, then we say that the series diverges. So our fundamental questions relating to series are, if we have a series, can we figure out whether it converges or not? Let's leave the question aside of what it actually converges to if it does converge, and let's just bring to the forefront the single question of, does the series converge? Does it make sense to first look at this infinite sum? And we'll leave the question about what does it converge to till a later time. So let's look at this series. The sum of 1 over n squared as n goes from 1 to infinity. And the question is, does this converge? Does this series converge? And we're given a hint here in this problem. Why don't we compare it with something we do know how to work with? We've been working with integrals so far in this term, so let's compare this series with the corresponding integral. Now, does it make sense to compare the series with the integral? We know the integral in some sense represents the area under the curve, and we know this series just represents a sum of these numbers, these 1 over n squareds for different values of n's. Is there a connection between them? Well, this is what we're hoping to find out here. So let's look at the diagram and just sketch some things in it. What I'd like to do is try to interpret this series as something geometric in the diagram. So I'm going to separate off these different slices under the curve. And what I'm going to do is I'm just going to look at some rectangles. So for each of these particular slices, I'm going to look at taking the rectangle where I've used the right-hand endpoint to get the height of the rectangle. And what that does is it gives me a number of shaded regions in here under the curve, and my question is, what is the area of each of these regions? What is the area of each of these rectangles in particular? So what's the area of the first one? Well, the curve here is labeled incorrectly. This should be, let me get the right color first of all. This should be a 1 over x squared. Let me write that a little bit nicer. Y equals 1 over x squared. And for this particular curve, 1 over x squared, at the value 1, x equals 1, the y value is 1. At the value of 2, the y value should be a quarter. It looks like what was plotted here was 1 over x, but 1 over x squared has roughly the same shape. This should be a quarter, so I'll just label the correct heights in here. At x equals 3, the height here should be 1/9. So instead of labeling on the axes, I'll just label the points here. So this is 3, 1/9, and this is 4, 1/16, and this is 5, 1 over 25. So what are the areas of each of these little rectangles? Well, each rectangle has a base of 1, and so the area is really just given by the value of the height. And so this would have area equal to a quarter, and this one would have area equal to a 1/9, and this one would have area equal to a 1/16, and this would have area equal to 1 over 25. And so what we find here is that the area of all the rectangles is just given by 1/4 plus 1/9 plus 1/16 plus 1/25 plus, well, that should be 125, not 124, 1/25 plus dot dot dot. Okay, I've purposely left off any sort of equality sign here because I'm actually going to do something with this expression in a second to warrant the equality sign unnecessary. So the area of the rectangles can be represented by this sum, which just happens to represent part of our series here. Notice that our sum is really starting when n equals 2. So this is really just represented by 1 over n squared. N goes from 2 to infinity. So we've managed to recognize that this series represents something to do with areas of rectangles. We've managed to make that connection. What else do we have? Well, we know that the area under the curve, under this curve, can be given by an integral from 1 to infinity of 1 over x squared dx. And here's the question. How does the series from 2 to infinity, or in other words, how do the sum of the areas of these rectangles compare to the area under the curve? Well, the rectangles all sit below the curve, so the sum of them has to be smaller than the integral. Okay, so what we found is that our integral is bigger than the series. In other words, our series is bounded above by this integral. Now the question is, does this integral actually exist? Is this integral a convergent integral? Does it equal some finite number? Is it infinite? Well, it'd be nice if it was finite, because then we could say that the series is smaller than some finite number, in which case it itself has to be finite. So here's the question. Does this integral converge? Well, we can actually work that out. So notice that this integral is equal to the antiderivative of x squared is negative 1 over x. And here we're evaluating from 1, well, I should say from 1 to m, and then take the limit as m goes to infinity. And in doing this, we get a value of 1. So what we've managed to find is that the area of the rectangles is smaller than the integral, and the integral is 1. So the sum is smaller than 1, in which case our series is smaller than 1. Okay, so you might argue that, well, wait a minute, that wasn't the original series. Okay, sure. Well, our original series was from n equals 1 to infinity of 1 over n squared. And so if I just add 1, because that's the first term, that's the term I've left off when I look at the series starting from 2. So if I just add 1 to this side of the inequality and 1 to that side of the inequality, then I get that our series has to be smaller than 2. Is this enough to guarantee it converges, that our series converges? Well, it is. And the argument is really to do with the monotone sequence theorem, which says that so our series converges when the sequence of partial sums converges. So now we take our series question and convert it to a sequence question from section 5.1. How do we know when a sequence converges? Well, one condition is if we have our sequence is bounded, so all our terms of our sequence are smaller than some value, bigger than some other value, and the sequence is monotone, meaning either it's increasing or decreasing, all the values are getting bigger than the previous ones or getting smaller. So if it's bounded and monotone, then it converges. And so when does a series converge? Well, we know it converges if the underlying sequence of partial sums converge. And so if our underlying sequence of partial sums is monotone and bounded, then we get convergence. And we have that here. We have that our series is bounded by 2. So any partial sum has to also be smaller than 2. And our series, looking at the partial sums of this thing, each sequence in that sequence of partial sum, or each value, or each term, I should say, in the sequence of partial sums, the next term is always slightly bigger than it because you're adding something more on. So Sn, our sum of our first n terms, is always smaller than Sn plus 1 because Sn plus 1 is just Sn plus 1 over n plus 1 squared, plus that next term being added on. So our sequence of partial sums are bounded. They're smaller than 2 and bigger than 0. And they're monotone because each term of the sequence is just slightly bigger than the previous one because it's obtained by adding something onto it. So all that really says is that we really need a monotone sequence theorem here. So by the monotone sequence theorem, since we know our series is bounded and monotone, it converges. Okay, so what have we done? What we've done is we've taken a question about series, which we didn't know the answer to, and converted it to a question about integrals, which we do know the answer to. And so this said that if I wanted to answer the question about whether this thing converges or not, look at the corresponding integral and see whether that converges. In this case it did, and it guaranteed that our series converges as well. Let's have a look at another example